Welcome to the DSA series. In case you're wondering what you're doing here, I'm sure you're interested in DSA, data structure and algorithms, which is why I've stumbled upon this video. In case you're wondering who I am, my name is Kallol Bhattacharya and I have been in the IT industry for the past 24 years, recently retired. And I thought that my knowledge in the IT industry is best put to use if I am with you and I'm trying to impart whatever I have learned in terms of these lecture series. DSA, Data Structure and Algorithm, is going to be an exciting series, and we will cover everything from the basics of DSA to the advanced concepts of DSA. We will cover a plethora of questions that are typically asked in the university curriculum. So anybody who is interested in DSA as a topic, as a subject, anybody who has DSA in their university curriculums, they can definitely benefit out of this. Be with me. I'm sure this is going to be an exciting journey in order to prove how and what modern algorithms can do. Thank you so much. Hello. Welcome back. We are into one more lecture on data structure and algorithms. And today we'll cover linear and circular queue. Good afternoon, good morning, good evening, depending on whenever you're watching this. What we'll cover today will be typically around the queue part of it, which is mostly to do with the linear and circular queue as a part of the syllabus that you see that we intend to cover for module 2. We have already covered stacks, and if you are interested, you may watch the previous videos in the playlist. But we will keep DQ and priority queue as a part of our next lecture series. Today's lecture will be around simple queues and circular queues. Simple queues, we'll call it as a linear queue, and then of course we'll cover circular queues. On those two topics, what we are going to cover? We are going to cover the operations of linear queues, the standard operations, the algorithms, the complexities around it. We are also going to cover the disadvantages of a linear queue, which prompts us to probably study circular queues. And in circular queues also, we'll study the same thing: operations, algorithms, and complexity. And further, we will wrap up the session using the time that we have to cover the solutions to mostly asked questions in your universities. That being said, let's start off with linear queues first, and then we'll get into circular queues. Now, I'm sure you would understand and appreciate the fact that this picture actually talks about a standard queue that you normally would see on the road. First of all, let me bound this queue by a boundary, right? So we are talking about this boundary. Let's count the number of people: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let us say that in this boundary, only 14 people can reside. Only 14 people can be part of this queue, right? Now, what we are trying to get at is certain properties, certain behaviors of the queue before we jump into the algorithm part of it. So while we know this is a queue, we definitely know that this person is going to move first out of the queue, right? So what is he? He had definitely entered the queue first, right? So he had definitely entered the queue first, and therefore he would be the first person going out of the queue, first in, first out. And that's the basic characteristics of a particular queue. And likewise, if I talk about this person entered the queue at the last, and definitely he would be getting out of the queue also at the last. So we can call it as a last in, last out. So either first in, first out, or last in, last out. You can call the queue to be exhibiting any one of these characteristics. That's the first point. The second point around this is that a queue will always have two open ends. The first open end here is for the exit. And this exit open end is going to be from the front of the queue. And the second open end is here, which we will call as the entry. And the entry will be at the rear of the queue. Every queue should have an exit and an entry, and every queue should have a tracking mechanism to actually track the exits and the entry, right? So those are the minimalistic behaviors that you need to remember about a queue. Now, once you understand this, let us deep dive into what are the operations that are possible on this queue. What are the things that can happen with this queue? So the first thing that can happen is that a person can enter this queue. So let's assume this is a person and that person can enter this queue is the first thing that can happen, right? And when that happens, we call that operation as an enqueue operation. So this is the first operation that we are talking about. Enqueue means that a person comes into the queue and goes to the rear and stands after the last person of the queue. So that's basically the enqueue operation. The second operation that can happen on this queue is that this person exits out of the queue, right? So this person exits out of the queue. So this person, when he exits out of the queue, this operation is called as the dequeue operation of the queue. Now, when such a thing happens, enqueue and dequeue, then as we understand, enqueue should happen from the rear of the queue and dequeue should happen from the front of the queue, because we know that those are the characteristics of the queue. Now, if instead of enqueue and dequeue, let's say that I am watching this queue, right? Let us say that I am watching this queue, and if I'm watching this queue, then I can actually track the first person in the queue, right? I can see that this person, let's assume that this person is still in the queue, right? And let us say that I can see this person in this queue through my eyes here, right? And all I'm doing is seeing this person. I'm not asking him to move out. I'm not doing this operation, right? I'm not doing the dequeue operation. I'm just watching this person who is first in the queue, and I'm just watching him that he is the first person in the queue. If that is the case, that operation, that watching operation is called as peeking the queue to see who is basically the first person in the queue. And this peek operation also happens at the front of the queue. So those are the three operations mainly that classify the behavior of a queue. Along with it, you have two helper functions, which is basically the first one, which says, is the queue full? So we initially said there are 14 people in this queue, and we had bounded this queue by these bounding boxes, right? So if this queue is bounded and 14 people can only enter, no more person can enter into the queue. 14 is the max size of the queue. So is full actually will return me with true if I pass it to this queue, saying that no more people can enter this queue. So that is one helper function that we will definitely need if we have to operate on this queue. And the last helper function is, of course, if there is full, there should be is empty. And that's the last helper function. So this last helper function will say that if I am removing every person from this queue, so this person goes out, and so on, right? Every person goes out of the queue through the dequeue operation, right? Then what will happen is that this entire queue will be empty. So no one will be here. The entire queue will be empty, right? So 14 will become 0, right? If that happens, then that queue will be classified as is empty, true. So these are the operations that are possible on a queue, and with these operations, we will now try to double click on each of these operations and figure out what are their algorithms, what are their time complexities, and what are they used for. So let us get into that mode now. We will start with a pretty simple algorithm, which is the isEmpty part of it. And for this simple algorithm, what we will do is, let us assume that a queue is implemented through an array, right? And that array max is at 5. So we have 4 pockets to this array, right? Rather, we have 5 pockets to this array. 4 is the index of the highest pocket. Now this array, as I said, is implementing the queue. So array is a structure with which we are trying to implement a particular queue. Now, as I said, that we have any queue is governed by most 2 important things, is that there should be a way to monitor the rear of the queue. We talked about this here. There should be a way to monitor the rear of the queue, and there should be a way to monitor the front of the queue. So these are the most 2 important things of a queue that we intend to actually maintain and recognize. So what we will therefore need to have is two pointer variables, front and rear. And because the queue right now does not contain anything, this is actually empty, therefore front and rear cannot point to a valid element in this queue because there are no valid elements in this queue. Therefore, front and rear will point to an index -1, which is an invalid index. Right? So front and rear is going to point to an invalid index in this queue. A valid index is of course 0, 1, 2, 3, 4, but that is only going to happen when there is some element in the queue. If there is no element in the queue, then there is no front, there is no rear. And therefore, we will mark it as -1 so that through is empty, we can actually return the front and rear of the queue. So with that, the front and rear of the queue, if we are actually maintaining it at -1, then what is the algorithm that we can actually produce in order to make this as an algorithm which will say that the queue is empty? We'll try to see this algorithm now. So net, when we talk about an algorithm, we will talk about the features that algorithm or the steps that algorithm will probably have. And when we talk about is empty, then we have already told that is empty will be classified by the front and the rear being equal to -1. Right? So we will therefore need to say that if my front or my rear is equal to -1, then under these two conditions, I will return is empty as, let's say, 1, right? And if they are not, then I will return is empty as 0. And that would be my is empty algorithm, right? So we are saying that front and rear are at -1, and hence the queue is empty. So I would return a 1 to the caller. I would say that if you get a 1, please assume it as a true. And of course, you know that a non-zero value is assumed as a true. So return 1 will be assumed as a true by the caller. And a 0 value will be returned if the queue is not empty, that is front and rear is not equal to -1. Right? So that is what we will attempt to do when we are talking about the algorithm of is empty. So this queue is empty, front and rear is at -1. We will say that if front or rear is at -1, remember that this is an OR condition. If front or rear is at -1, right, we will return a 1 stating that the queue is empty. Else we will return a 0 which will state that the queue is not empty. That means front and rear are pointing to a valid element. We will see those cases now. What is the complexity of this? Neither of these statements, none of these statements are dependent on the size of an array, or on the size of this particular array. That is, the time complexities do not increase. The complexity of time does not increase with the size of that array, which means that the time complexity will be an order of 1. Every statement will be executed in a fixed order of time. Similarly, the space complexity will also be an order of 1. There is no necessity of defining more spaces as the size of the array increases, and hence both time and space would be an order of 1. If we move into the next operation, again we'll take a simple one, is full. Assume that we have some elements in this queue like this. Let us assume that we have some elements in this queue like this, right? And this is my index of the queue. And mind it, we have already assumed that we are going to take an array to represent the queue, right? And we will assume that this particular end is the front of the queue, right? And this particular end is the front of the queue, and this particular end is the back of the queue. Right? So this is our assumption, that the front of the queue and the back of the queue is like this. And with this in mind, can we say therefore that the front of the queue, which is at 27, means that our variable or pointer, that is the front pointer, is right now at 0, right? Definitely we can assume that. And can we therefore also assume that the rear of the queue is described through another pointer which is called as R, and it is pointing at the index position 4, which is evidently the back of the queue. So as I said, for a queue, we'll have to remember most two important things, that we have to track the front and the rear. Unlike stack, why? Because in stack, we have to only track the top, right? The queue in a stack, the push operation was at the top, the pop operation was from the top. One variable top was doing both the operations. But here, there is one variable which will track the exit, one variable which will track the entry. Exit is through the front, being tracked by the variable front, and entry is through the rear, which is tracked by the variable rear. And we are calling them as F and R here, just for the sake of simplicity. Now, if we have understood this, do we now understand that with max equal to 5, F is where? F is right now at 0 and R is right now at 4. And max is at 5. We know that, right? But we also know that no more entries into the queue can be possible. No more enqueues into the queue can be possible. And therefore, can we say that our R, somewhere this R should give us a logic to say that the queue is full. And the logic is that my R should be equal to my max minus 1. So if I can detect that my R is equal to max minus 1, it would imply that my queue is full. So if R equal to max minus 1, I'm going to return a 1, which is a true, that is yes, my queue is full. And if it is not, then I'm going to return a 0, which means my queue still has options for an entry. That means R has not reached here, R is probably here or here, and hence I can insert more items into the queue, right? Until and unless R goes to the end of the queue is still not empty. Sorry, the queue is still not full. And therefore, R moving to max minus 1 would mean that the queue is full. No more items can be entered into the queue. What is the complexity of this? Again, we will have a time complexity of order of 1 and a space complexity of order of 1, because none of these statements are having an influencing factor depending on the size of the array. All these statements will be executed in a constant amount of time. The array size has nothing to do with it, right? So my time complexity and space complexity would be order of 1 for this. Now, if we move on to the next operation, and this is the important operation that we are talking about, which is an enqueue operation. Now, to do an enqueue operation, let us break down that enqueue operation into 3 phases. Phase 1, we would have front and rear at -1 when this array is empty. We have already discussed that during our is empty discussion, right? So when we have front and rear at -1 pointing to the queue, and don't forget, this is your front, right? This is your front and this is your rear. We will not forget this. And now the queue is empty. Our front and rear pointers are pointing to -1. And our array index is like this. We are implementing a queue through an array. Max is set at 5. Right? So with this in mind, if we start the operation of the queue and we say that we have to take 27 into the queue, right? So what will happen? This 27 will come and move all the way here, right? But do you think before 27 comes and moves all the way here, let us assume that the queue already had some elements like this. The queue already had some elements like this. Now do you think that the queue can get this 27 inside? It cannot, because the queue is full, right? Your front is here, but your rear is here, and rear is equal to 4, which means rear equal to n minus 1 or max minus 1, and therefore the queue is supposed to be full. Therefore 27 cannot enter. So our first check whenever we try to do anything inside the queue, whenever we try to put any element inside the queue, is to check whether my queue is full or not. That is my first check. So if my queue is full, I will return back to the caller a -1, signifying that something is wrong. I could not push or I could not enqueue this element into the queue. Something is wrong, right? So I will return -1 to the caller. So that is my first step. The second step for me will be that if I come back to our empty queue concept, right? If I come back to our empty queue concept, then my front and rear are at -1. So if this 27 wants to enter, then 27, in order for 27 to enter, my rear has to move from -1 to rear ++, so that it starts pointing here at 0. And then I will be putting that my element 27 would be actually going there, right? So at the position rear points to, which is 0, 27 will actually move. So 27 is coming and putting itself into an area where rear currently points. So we have to do a rear ++ so that 27 can get a placeholder. From -1, it should go to rear ++, right? And if you think about it, if we then have one more element coming in, let's say 39, then because rear ++ has taken my rear to here, another rear ++ will actually be taking my rear to here, right, which is at 1, and therefore this 39 can easily enter into the newly pointed rear index. So 39 can easily come here. So can you see what is happening? What is happening is rear is moving, right? Rear is moving, and rear, the new position of, or the last position of rear is here. In this way, rear will move here to here to here and become full. That is, the queue will become full as and when we push more elements. But where is our front? Our front is still at -1. Don't you think our front should be here? Right? Our front should be at 0 always, right? And when I say always, of course, if you have not done a dequeue operation, we'll come to dequeue in the next slide. But when we are actually starting this operation and 27 is the first element that is getting inserted, right? Let us go back to the first situation where 27 was supposed to be inserted, right? During this process where 27 was supposed to be inserted, our first step therefore would be that while we understand that every enqueue operation will increase R to R++ and then put the element in that R++ position, but there is no one to actually increase front. But front should be increased to 0 at least the first time it hits, right? So the first time initialization, so we will have to check that if it's a first time, which means that if my front equal to -1, if my front is equal to -1, then I should be making front equal to 0, right? So that is my first time initialization of the front, which is necessary because enqueue operation does not increment front. It increments the rear. As you see here, rear will be incremented and the element will go to the new position of the rear. Front will not change. So at least for the first time, front will have to be set to 0 so that the queue pointers are in their correct positions. And that's why we will do this particular step. Then comes our case 3. And in this case 3, what we are trying to do is the same thing that we have written here, that while front is now at 0, we should be in a position to increment R and then say that my array R that is my rear, is equal to the element that is supposed to be inserted. So r plus plus from -1 will take r to 0, and therefore ARR of 0 will become equal to the n, and n in this case is 27. So 27 will come and sit here. And if we take a 39 as the next element to be inserted, then another r plus plus will happen here, right? Case 3 will fire again, another r plus plus will happen, r will start pointing to here, and therefore ARR of 1 will be equal to 39. 39 will come here. So I hope you can see what is happening. R is moving to the right and front is here pointing to 0. So the front of the queue is 27, the rear of the queue is being pushed from 27 to 39 to another person enters, let's say 5, then another r plus plus will happen here. And this element will therefore move to 2, and this 5 will find its place at the rear of the queue. So the rear is moving, the front is static at 0. And that's basically Enqueue. As I said, Enqueue does not touch the front, only the rear gets moved. So at least for the first time, in order to position front in the correct position, we will do a front equal to 0. Complexity of this algorithm again remains the same. None of these steps are influenced by the size of the array. Therefore, the time complexity is going to be order of 1. The space complexity is also going to be order of 1. Right? So that is Enqueue for you. If we actually see a dequeue operation, then from a dequeue operation standpoint, it actually means that a particular element from the queue will be moved out from the front of the queue. Don't forget, this is my front of the queue, and don't forget, this is my rear of the queue. Right? So if we assume that 27 is an element here, let me mark the indexes. If we assume that 27 is an element here, and these are my values, then my front is pointing here, my rear is pointing here. And when we say a dequeue, and before we get into dequeue, one important thing that I wanted to tell you is that, remember, from a remembering standpoint, the tip is that an Enqueue has 3 things to check, right? We have discussed those 3 things. Similarly, a dequeue will also have 3 things to check, right? Now, before those 3 things to be checked, if we actually just come back a little bit, right, and we talk about front and rear to be -1, can a dequeue happen? Can we move out an element from the front? Dequeue is moving out an element from the front. When front and rear is -1, what does front and rear -1 mean? The array is empty. The queue is empty. So we cannot do a dequeue. So our case 1 will be definitely to check whether the queue is empty. And if the queue is empty, we will return a negative integer to signify something is wrong. And if the queue is not empty, then we will not return anything. We will just move on with what we were doing, right? So it's not about returning anything. I hope I did not return anything in the full. Yes, I did not return anything. So net, yeah, this is also okay. This is also okay. Okay, fine. So net, what's happening is that in the dequeue operation, I have checked for is empty, and I have returned -1 if my queue is empty. Right? Now, what we need to also now ensure is that we need in fact, I was telling you earlier that Enqueue has 3 steps. From a remembering standpoint, Enqueue has 3 steps. Similarly, dequeue will also have 3 steps. We have done the first step. Our second step for dequeue, and to do the second step for dequeue, we have to assume a situation when the queue is just about to get empty, right? So let us assume that the queue is just about to get empty. How do we reach that stage? Let us do some operations on the queue. Let us say that these are the elements in the queue, right? I have enqueued it, and now my front and rear are no more at -1. Front is here, rear is here. Now I'm dequeuing. If I dequeue, right, what should happen? Right, we will come to the way in this dequeue happens. But when you understand dequeue, right, the front, the element at this particular index, which is the front of the queue, should move out, right? Now, what is happening is that the element is not moving out. Our front is moving forward, right? So if I have my front here, which was at 0, I will be moving front here because I will do a plus operation on front. And because I do a plus operation on front, this element will move forward. And now there is nobody pointing to this 27 or the 0th index of that particular queue. And therefore, what we have now is that this element is assumed to be logically deleted. When I say logical, the array still contains it, but the queue does not contain it. Because the queue is a representation of the array marked with the front and the rear, and the front is not pointing to that. The front has moved forward, front will never go backward again, and therefore you will never be able to access 27 again. So this element is as good as gone. Right? So from now onwards, for all practical implementations, we will wipe away this element just to make sure we understand that we have actually logically deleted this element from the array. Mark my words that we are not physically deleting the element from the array, we are logically deleting it. From a simplicity sake, from a visualization standpoint, I am just trying to make you understand that we have an empty pocket now in the array. Now the front has moved forward because we dequeued an item from the queue. So 25 has moved out, 69 is the new front. The rear is not moving, right? And if we actually do one more dequeue, then this front will do another plus and will move forward here, which would mean that this element will be logically deleted. Our new front will therefore become here, right? And if we still do another plus, our new front will come here. And this element will also be logically deleted. And we said that we will, for all practical purposes, remove these elements, right? And that's what we have done. And if we do one more dequeue, then this front will come here, which means front and rear will now point to the same index. What does this mean? This means that there is only one person in the queue, and that is 77. So front is 77, rear is 77. So that's what this means. So every dequeue is actually changing front. Every enqueue is actually changing rear. So you saw here, every enqueue was actually changing the rear. The rear was moving forward. And every dequeue is actually changing the front. The front is moving forward. So if you understand this, now you can see that rear and front are at the same area. Now can we say that if rear and front are at the same area, another dequeue means what? This will be moved out. So this becomes a logically empty area. Where will rear and front go now? It's an empty queue. So rear and front goes back to its starting point, which was -1. So this is what I wanted you to understand, that when rear and front are the same, that means you have the last element in the queue. One more dequeue will make rear and front go back to -1, which was its initial condition. So that is your case 2. That if my rear and front are the same, then make my rear equal to front equal to -1. So that is what I would say as the algorithm for the case 2, right? And all this while, case 3 we have already discussed, right? What were we discussing? We were discussing that in case 3 we will, what is case 3? Let's take case 3, right? Let us take the the pushes that we had done or the enqueues that we had done. Let's say these are the enqueues we had done. Where is our front? Where is our rear? In this situation, our front is here, our rear is here, right? So if front and rear are here, then what are we trying to prove now? We are trying to say that if a DQ happens, this front will move forward, right? So if a DQ happens, this front will move forward. But before that, don't you think that this element will have to be coming out, right? So before that, this element has to come out. So what we will need to do is that 1 minute, let me just push this down so that I get some space. Yeah. So let us take this element. Let us take this element out initially. So if you remember in our last case, when front and rear were pointing here, right, we had said if rear is equal to front, then please make rear and front -1. But if we make rear and front -1, it will come back here. This element will not be able to dequeued. So we will have to store this element for us to dequeue it before we move rear and front to front. So we will say that let us take into a value variable ARR of ARR of front, right? So this is what we will say, that we will take you basically the element that is being dequeued into a value variable, and then we will adjust our pointers. And in case 3, what is happening is we have moved the front here, but before moving the front, value is already at ARR front. Remember, we had front here originally, front was pointing to 0, so value ARR front was 27. So this still has 27, and thereafter what we can do is we can move front to front plus, right? So once these 3 things are over, we can therefore return the value as the dequeued element back to our caller, right? So that is how we will interpret the dequeue operation. One more time, if I repeat what we discussed, we said that dequeue and enqueue, both of them will have 3 operations or sub operations to consider. In dequeue, the first operation of course will be if we have to dequeue something, if we have to take out something from the queue, then definitely the queue should not be empty. If it is empty, we will return -1, right? So that's what we will do. Next, what we will do is wherever front is, we will extract that value from the array and put it inside a value variable. Wherever front is, it might be here, it might be here, it might be here, it might be here, wherever it is, because our job is to dequeue from the front, right? So we will dequeue from the front. First step of the dequeue will be what? Store it inside a variable so that we can send it back to the caller. So we are storing it inside a variable. Now there can be a special case where front and rear yeah, so where front and rear are both pointing here, front and rear are both pointing here. So there is some element here, which is being pointed by front and rear, right? We will definitely need to dequeue this. So this has already gone into value. But then there is no point of front and rear being here, right? Front and rear therefore needs to come back to becoming front and rear equal to -1. And that's what we have done here. So if rear is equal to front, that is front and rear are same, right? Then make front and rear -1. Because you have already extracted that element, now there is no job of rear and front because the array is empty. So the array is empty means you'll have to signify it with this particular status. And if it is at any intermediate position, let's say it is here, right? If it is here, then you are going to move it here, and that's a simple front plus. And therefore front will come here and point here, and this element becomes obsolete and it is no more there. This was anyway obsolete, this is obsolete now because front has moved to rear. So once you are done with the pointer movement, right, you are done with these pointer movements, you are now free to return out of the function with the value that you just now dequeued, right? So that's why this return is essential for the value that is stored here. And that's the simplistic example or explanation of the dequeue function. What is the time complexity? Every step here is not bounded by the size of the array. So the time complexity is an order of 1. The space complexity is also an order of 1. Right? So that's your dequeue function. Now peak, as I said, again, don't forget, this is your front of the queue and this is your rear of the queue. And peak wants to just see this element. So peak wants to see this 27, right? Let us say we have these elements in the queue at 0, 1, 2. My rear is here, my front is here. So peak just wants to see this element. So in peak's case, what we are supposed to do is that if I want to see something, or if I want to read something from the queue, first check is, of course, that my queue should not be empty. If it is empty, I can't read, right? So if it is empty, I will return -1. And then if it is not empty, then I will just return the element at the front position of the array. That's all. So I'm supposed to just see the person who is standing in the front, and I can see it through this particular syntax. I don't need to change front, unlike your dequeue operation, which does a front plus plus to take front here. We will not do that in peak. Peak is not supposed to do that. Front is supposed to stay there because we are not removing that 27 out of the queue. So this is the algorithm of peak. Complexity of peak is Tn, again, will be order of 1, Sn will be order of 1, and these will be as per the guidelines that we do not have an influencing factor on the size of the array. Now, if we summarize what we just now did, right, and we try to probably put these elements into this. Let us see if we try to put these elements into this. So let us put 20. Again, this is the front of the queue, right? We should not forget that, from which the exits will happen. And this is the rear of the queue, from which the entries will happen, right? Now, we are saying Enqueue 20. Now, what happens when we say Enqueue 20? The queue is empty. Just see this equation the algorithm represented as a C code here. What is happening? You are saying Enqueue what? Enqueue 20. So value is 20, right? It is checking whether the queue is full. Because you are putting some item into the queue, you need to check whether it is full or not. And you remember we said Enqueue has 3 operations. These are my 3 operations. First operation, second operation, and my third operation, right? And likewise, dequeue will also have 3 operations, as I had said, and that's the easiest way to remember it. Now, what is happening when Enqueue is happening with 20? We are checking whether the array is full. Of course, we have to check, otherwise we cannot enqueue a particular element into the queue if the array is full, right? So how do we check it? Is full gets fired. Now, is full does what? It does this. What is this? This says, is rear equal to max -1? Where is my rear? My front and rear is right now at -1. So rear definitely is not equal to max -1 because my max is at 5, right? It's a 5 element array. So rear is -1, whereas max -1 is 4. So -1 is not equal to 4. Therefore, is full will return false. So it will go to if front equal to -1. Yes, front equal to -1. You remember we said that in the first iteration of Enqueue, we need to set front because Enqueue only rear changes. Front doesn't change. Front changes during dequeue. So how will Enqueue ensure that front points to the front of the queue when the first element is entered? So it will make front equal to 0, right? And that operation will actually be done here. So this is what will be valid and executed when we do this Enqueue 20. Because the queue is empty, front was -1, front became 0. So front is right now pointing here, right? So that is this particular line, the second operation of Enqueue. The third operation is Q plus plus rare equal to value. So we had discussed this earlier that we have to do an R plus plus, right? We have to increment R and then say that the Q, whatever that Q is, in this case ARR is the Q. Here I have taken Q as a variable. I hope you can understand the difference here. But then what is going to happen is we are going to say that rare was at -1, plus rare is do the increment first. So rare becomes 0. So therefore rare now, because of the plus rare, will move here. And the value is 20. So the 20 will be assigned here for this particular operation. So this will also be a valid operation, right? Now, that's your Enqueue. What happens when Enqueue 4 happens? When Enqueue 4 happens, is the queue full? Of course it is not full, because rare has not gone till 4, right? Rare has to go to max -1. So this is again false. Front equal to -1 will never be true till the queue becomes empty, right? So the first time it has become -1 to 0, it will never become -1 till the queue becomes empty. So this is also false, and therefore R plus plus will happen, and R will move from here to here, and we will be putting at that position the enqueued value, which is 4, right? So that is what will happen when we do an Enqueue 4. When we do an Enqueue 41, a similar thing will happen, and we will push it here. Enqueue 67 will take it here, Enqueue 5 will take it here. So all of this time, what is happening is full is returning with false, front is returning with false, and all the insertions are happening properly, right? So we have done how many Enqueues we have done? We have done 5 Enqueues. So there should be 5 ticks here, right? And 5 times this check would have happened, right? And is full would have returned false every time. 5 times this front check would have happened. 4 times it will return false. Only the first time it will return true. And by this time, R would have moved to this particular position. So that is what happens when we actually are talking about the first 5 Enqueue of this queue, right? As per whatever we have written in the algorithm. Now, if we do a DQ here, this DQ that we do will be moving this front to the positive direction. But before that, the DQ will check whether I can DQ, whether the queue is empty or not, right? Of course, the queue is not empty. But how does it understand queue is empty? By this syntax. Front or rare should be -1. And this is the same algorithm that we talked about when we talked about is empty. So it is checking whether front and rare is -1, that initial condition, which is no more valid. The queue is right now very full, right? It's actually full. So is empty will return -1. So this returns false. So what we are saying now, that this front position, wherever it is pointing, we will extract this and put it inside something called as value. So this is what is happening here, right? So this value will therefore be 20, because front is pointing to 0 and value at that is 20. Now what we are saying is that if front equal to rare, so this was my first condition that we checked. This is my second condition that we are checking. That if my front equal to rare, you remember we had discussed when front equal to rare, there is only one element, front and rare are the same. Therefore, the queue is about to become empty. Therefore, make the queue empty by using front equal to rare equal to -1, because you have already taken out that value. Therefore, now you can move the pointers. Moving the pointers will not make sense now because front and rare are pointing same where. So move the pointers to an initial state of the queue becoming empty, because you have taken out the last value into value, right? So we don't have that situation here. So this will be a cross. And front +1 means that this front, once we have taken out this 20 as value, this front plus or front equal to front +1 will move it here. So that is what will happen when this first DQ happens, right? So this is going to be front +1. And this is my third operation. Okay, so as I said, Enqueue has 3 operations, DQ has 3 operations. right? And we talked about those three operations here. If we do one more DQ, what will happen? Is empty is of course not true. Front equal to rear is of course not true. And therefore front moves one step forward, right? And value will be DQ'd as 4. Next time we do a DQ, this value 41 will be DQ'd and front will move forward. So every time what is happening? This is failing, this is failing, this is succeeding. And the fourth time that we do a DQ, my value will be 67, which will be DQ'd, right? And front will move forward to R. So front is no more here, front moves forward to R, right? And therefore we have this as the fourth step. This is a cross, this is a cross. So this is what happens when the 4 DQs happen. Now, ultimately what will happen is front and rear are pointing here. And next time, if we want to actually enqueue a particular item, right? If we want to enqueue a particular item, rear is pointing to 4, right? I hope you understand that enqueue checks for is full first. And because is full will return true because rear is pointing to 4, which is equal to max minus 1, right? And therefore enqueue will fail. Enqueue will say no further space in the queue. But do you think that we have DQ'd these many items from the queue, right? All of these items we have removed from the queue. All of these items we have removed from the queue. Therefore, these items are no more there in the queue, right? So if these items are no more there in the queue, then why is the queue being returned as is full? You already have space here, 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 here. Why can't you put one more enqueue? Because enqueue logic says that a queue is full if rear equal to max minus 1. So rear is max minus 1. And therefore the queue is full, nothing doing. Front cannot go back. Front has moved forward. And front and rear are now pointing to the same area, right? So this is where the problem comes with respect to a linear queue. There is a wastage of space here. While there is still space here, you cannot do anything. You cannot enqueue a fresh element because rear is now pointing to max minus 1, right? You cannot. And of course, if you DQ this, then this 67 now becomes the new DQ will be 5, right? And if you have DQ'd this, then F and R are actually the same. So this particular condition will fire, right? So this particular condition will fire, and which will make front and rear equal to minus 1. So front and rear will become minus 1. This element will not be there. The array is empty, and then you can start doing your enqueues. But remember that if you had an element here, with front and rear pointing to the same area, then this particular condition would have prevented you from going forward, right? Which means these spaces are there but not for you to consume. You cannot consume that. And that basically brings me to the disadvantage of a linear queue, which is wastage of memory, right? You have memory here, you have free space here, but you cannot enqueue a fresh element because front and rear are now pointing to 79, and which is basically the last element of the queue. And because rear is pointing to the last element of the queue, it is thought that the queue is full, irrespective of the fact that front has moved forward. Now, what does that mean? That means that you have stopped entering any further elements. That means you have a limited number of insertions. You cannot insert any more items, right? So at some point you will be limited by the number of insertions you can make into a queue, because your rear will have pointed to the last element, last pocket of the particular array. So when you enqueue in such a manner, enqueue, and reach the end of the queue, then you have exhausted all your insertions. You cannot insert any more items in a linear queue unless you dequeue the last element, right? If you dequeue till the last element, keep the last element static, still you cannot actually enter any more elements, because the last element is still pointing to, rear is still pointing to the last element, and because rear is pointing to the last element, the algorithm thinks that the queue is full, right? So that's the limitation. When you reach the last element through an enqueue process, your rear has moved to the last, and hence it is counting the queue to be full. You cannot do any more operations. You can do dequeues, but you cannot do enqueues. And if you do a dequeue till you actually empty the queue, then again you can start the enqueue process. But definitely you are limited by the number of insertions. And that's basically the disadvantage of a linear queue, which prompts us to actually move into a circular queue model. So what was happening? What was happening is that we were unable to utilize these spaces, right? We were unable to utilize these spaces which were left empty, because front was moving forward from here. Front was here, it moved here, then it moved here, then it moved here, then it moved here, right? Now front has moved forward and rear is already at the back, right? Because of all the enqueues happening in the beginning part. So now rear is at the back and hence the array is full, but front has created spaces which cannot be used because front cannot move back, right? And neither can rear move back. So this is the problem of a linear queue. So what we will do is, we will therefore study a circular queue which basically alienates this problem. Now, how does it remove this problem is what we will first investigate. Now, let us assume that, and I hope you can understand that this is the same array that we had taken to implement our queue. And this same array, if we enqueue 20, if we enqueue 4, 41, 67, and 5, then it also means that if I stitch this 4 with this 0, right, we are creating something which is a circular queue. And when we do this in a circular queue, then we can imagine this same array to be treated like this visually. Visually, can you imagine this array to be a circle like this? That at the 0th pocket, you have 20. First pocket, you have 4. Second pocket, you have 41. Third pocket, you have 67. And fourth pocket, you have 5. So this is your queue, right? And this is a circular queue. Nothing fancy about it. All we have done is we are imagining that after the 4th index, the 0th index comes back again. After the 4th index, the 0th index comes back again. And that is where you are stitching this 4th index with the 0th index to make a circular queue. Now, if you understand this concept, then let us imagine what is happening when we do a dequeue. When we do a dequeue, where is our front? Where is our rear? Now, when we had done this 24, 41, 67, 5, don't you think our front is here, our rear is here? So does that mean our front is here at 0 and our rear is here at 5? Of course it means that. What does it mean? It means that from the front to the rear, the queue actually looks like this. From the front to the rear, the queue actually looks like this. So the front to the rear, if I walk down from the front of the queue, I will get 20. Next person will be 4, 41, 67, and the last person will be 5. And that's what this array is also saying. That's what this circle is also saying. So you have to be very careful when you are thinking about that circular circle. Where does front start? Where does rear end? Right? And that's what I have drawn on the screen here. So if you can understand where does front start, where does rear end, then the job becomes easy. That we now know that front starts here, rear is here. Now we are doing a dequeue. Dequeue always happens from the front. Dequeue will always happen from the front. Front will move forward is what we know, right? So that's what we know. So if we know that, then let us move front forward. Let us remove this element because this is being dequeued. Let us move front forward, right? So we have removed this element from the queue. Front has moved forward, pointing to right now 4. So front is right now here. Front is no more here. right? And we have logically removed the element from the queue, right? So if we have done that, then our job is now to actually understand that, let me remove this so that I can explain now. So we now have our rear here, our front here, right? And what we are seeing is that before front there is an empty space, because front has moved forward. This empty space got created because front moved forward. Before front there is an empty space. So if I can basically say that there is a reason for us to believe that if I can move the element forward when I get a fresh enqueue, so if I get a fresh enqueue request, then I should be able to move this rear here so that I can insert the new element into this blank area. And that is what circular queue tries to achieve. That whenever a fresh enqueue will come, rear will increase irrespective of rear is at the last or not. Because this is no more last, this is a circular queue, right? So it will go around the queue, wrap around the queue, it will wrap around the queue, and it will go to the first element and see if it is empty. It will insert the next element, next person into the queue. And that is what we will try to achieve, and that is what is a circular queue. That a circular queue is trying to make the best use of the pockets that are being created by front moving forward, that is by the DQ process. Each DQ is creating a blank space, and that circular queue will actually try to utilize this blank space to insert more and more elements instead of saying the stack is or the queue is full, unlike the linear queue. So that's what is the mechanism of a circular queue, and this is exactly where we left off. We are saying 24, 41, 67, 5 was enqueued, then we did a DQ. So because we did a DQ, right? Because we did a DQ, our this spot became empty, right? This spot became empty because front was here, front moved here. Because front moved here, therefore this spot can no longer be accessed, because right now my front is here, my rear is here. So now if I do an enqueue, right, 79, what should happen? My rear should move forward, right? You remember rear used to move forward here, right? And therefore Q rear equal to value. So rear should move forward also here, right? And Q rear will become the new value that is inserted. So we can make use of this space. But there is a problem. If we increase rear, R is at 4, R++ will make it 5, and this is an invalid index. There is nothing called Q5 or ARR 5, right? So there is nothing called as ARR 5. So all we have here is a 0 after R equal to 4. Let's assume for the time being, let's assume that R is here. When another enqueue happens, R can be easily made ++ to move here. So if R is 0, changing it to 1 will happen through R++. If R is 1, then we can do an enqueue by moving R to the next element very easily by changing 1 to 2 by using R++. And that is what is happening here always, right? If R is 2, we can easily change it to 3. If R is 2, we can easily change it to 3 by doing R++. If R is 3, we can easily change it to 4. If R is 3, we can easily change it to 4 by doing R++. What am I trying to say? I'm trying to say that a simple ++ can move my R to the next position to allow for insertion into the queue. But when we are at 4, we cannot do an R++ to move ourselves to 0, because we have to move from 4 to 0, right? And 0 does not happen by an R++ from 4. So it will make it 5. So from 5 we have to reach to 0, and the way to do that is say that all of this should hold true, plus when I do a plus on 4, it should become 0. How does it happen? 0, when it is 0, 1, 2, 3, right? A plus on any of these will take me to 1, 2, 3, 4. And when it is 4, a plus on that will take me to 0. This only happens if we do an R+1 modulo 5, right? You have to take the remainder of the division with 5, because there are 5 elements here. We will do a R+1 modulo 5. R+1, why? Because that's my new place. This is my new place. My R was here, +1 will take me to my new place, but my new place may be an invalid index. So do a modulo with 5, I will get a valid index. So let us see what happens with R+1 modulo 5, right? We will do the maths here for most of the cases, and let us see what happens here. So if I do, and if my R is at 4, right? If my R is at 4, then R+1 is equal to 5. 5 modulo 5 is equal to 0, and that's where I wanted R to be at the 0th index, so that it can now start accepting more enqueues. So this enqueue will therefore move here. And that is what we have written here, that rare will be rare +1 modulo max, and then we will do a q rare equal to value to put that value in the appropriate position. So we have to change this particular enqueue function, which was basically our linear queue, to a circular queue algorithm like this, right? And the only area we change is these two lines, this line and this line, so that my R moves forward, but is basically not just moving forward blindly, it is also doing a modulus so as to stay relevant to the index of the array, right? And if we had R somewhere here, right? If we had R somewhere here, right? Then also if we did this rare +1 modulo max, so R is at 1 and R +1 is 2, and therefore if we do a 2 modulo 5, that's what exactly this syntax says, we will actually get 2 again, which is my remainder of 2 division 5. So where does R move? R moves here, and that's what we want. We want R to move here, right? And instead of just saying +1, we'll do a modulo 5, so that if it flows out of bounds, it will come back again. And that's what we mean by doing this, right? I hope this makes it clear in terms of how a circular queue is operating and trying to utilize the space created due to the dequeue process, which is moving the front and creating spaces here, right? So that rare can be used, we are actually moving rare in this manner. Every enqueue now can use rare in this manner, so that rare moves forward and takes over the blank space that has been created. So if rare moves forward, then front will also have to move forward, right, into a blank space. Let us see that example also, right? Let us say that 10, 20, 30, 40, 50 is actually pushed or enqueued here. 10, 20, 30, 40, 50 is enqueued here. So this is my front. This was the first element to be pushed. This was the last element to be pushed. So the queue goes around like this, right? So the queue goes around like this from front to rear, right? Now, if the queue goes around like this from front to rear, if you understand that the queue goes around like this from front to rear, let us try to do these operations now. Dequeue. Now what will dequeue do? Dequeue will take out the front element. This element will no longer be there, and front will move forward. So front will move forward you have one more DQ, one more DQ, one more DQ. So 3 DQs. So we will have this going away, this going away, this going away, and front moving from here to here, here to here, and front moving here finally. So the front will not be anywhere here. Front and rear will now be pointing to the same location. I hope you understand that our front was here originally. We made 4 DQs. So the first time front went here, second time front went here, third time front went here, fourth time front went here, and now front is sitting there. So all these fronts have been removed or moved into this particular 4th index position, where front and rear are pointing to the same element, which means we are at the last element of a queue. That is front and rear. There is only one element in the queue. Front and rear are the same, right? In that situation, if we do an Enqueue, then this Enqueue should do what? This Enqueue should increase the rear of the queue, and should put that element in this blank spot, which is 60, and increase the rear of the queue. How will it will do? We have already done that. R plus 1 modulo 5. So we will get 0, right? And that Enqueue therefore will happen at the 0th index. So R will therefore not be here. R will move from here to here, and 60 will be enqueued into this position. Now front is here, rear is here, right? What is happening? Front and rear, the relationship between front and rear is this, right? This is the front of the queue, this is the rear of the queue. If you move forward, it will look like this. I hope you can see that this is always moving in an anti-clockwise direction from front to rear, right? Now, if I do a DQ, right, what will happen is the front will move forward. So front has to move forward. This element will have to be DQ'd. Front will have to move forward, but front cannot move forward because front plus plus moving forward will make what? Will make 4 go to 5, and 5 is an invalid index. The same way for rear. So the same way for rear, we will do this. Front plus 1 modulo max, and the same logic will be applied. So 4 plus 1 modulo max is equal to 0. So the new front will be 0. So front will move from 4 to front 0 here, right? So that DQ will take front and rear back to 60 again. That is the last element of the array is there. So front and rear pointing to the same area, but you have seen that front is also now moving forward, right? Front is trying to move forward beyond 4, that is going to go to 0. And of course, if front was here somehow, then this logic still holds good, because if you do a DQ, then front will have to move here. So front was 1 plus 1 modulo 5 is what we have to do. Front plus 1 modulo 5. That is what we will do, which is 2 modulo 5, which is equal to 2, and therefore front will move to 2, right? So this logic works for 0, 1, 2, 3, but for 4, a special case of modulo 5 will take it to 0. That's what we are interested in, and that's why we made this change to the logic of a linear queue. So this was a linear queue, and we made that logic change to a circular queue. So we have discarded this in a circular queue. We have just made this small change in order to make a linear queue into a circular queue. So I hope you are getting things in terms of what we are changing in order to make in order to build a circular queue and the algorithms around it. The last part of a circular queue, which we still need to change, 3 things we had to change from a linear queue perspective. We have done 2 things. We have done an Enqueue change and we have done a DQ change, but we also need to do a full change, because the logic of full, rear equal to max minus 1, will not hold good. We'll see why. So let us say that 24, 41, 67 and 5 is what we have enqueued, and this is how your circular queue looks like. If we do one DQ, what will happen? Let us say our front is here, our rear is here. We do one DQ, front will move forward. So front will come here, right? So front comes here. Now we do an Enqueue of 27, right? If we do an Enqueue of 27, if we do an Enqueue of 27, my rear, I know that rear can move forward because in the Enqueue definition, in the Enqueue algorithm, we have already said rare is equal to rare plus 1 modulo 5. We have already said that. So I know in Enqueue we are good and rare can move to 0. But if you remember, this Enqueue checks whether first the array is full or not. And that is where it will fail. Even before it can reach here, this will fail. Because is full works on this algorithm. So is full says rare equal to max minus 1. Rare is here. Is it equal to max minus 1? Of course it is 4, which is max minus 1. So you cannot actually implement this algorithm at all unless you change the is full logic. So is full logic also needs to change in the same manner. What is the manner here? That if we increment rare, there are chances rare will cross. So do a mod. There are chances rare may not cross. Even if we do a mod, that is also perfectly fine. For example, if rare is at 2 and we do a plus 1, which is here, then we reach to 3. 3 modulo 5 is still 3. So we have not changed anything. 3 modulo 5 is still 3. Right? So if we are actually at a position where, if you imagine the situation where we were, we will just remove this and drew a clean slate of the situation where we were. We had done all of these Enqueues, then we had done a DQ, which was meaning that this particular element was not there, front had moved here, and a rare was here, right? And we were saying that we wanted to do one more Enqueue. That is where we were. And this Enqueue, while rare can move is what we understand, but before rare can move, is full is checked. And rare being at 4, it is equal to max minus 1. Therefore, is flow is true is true. Is full is true. So what we can do is, we can say that if we make the rare increment it by 1, if we increment rare by 1 and then we compare it with max, right, then we can actually say that if the rare and the max are found to be the same, then they would be in a situation where we can say that the rare and max are going to be depicting a full queue. So the situation I was showing you, that a DQ has happened, this DQ has happened, this has moved forward. Now if I allow this to move forward, if I allow this, if I make this change, what will happen? Let us see. Rare plus 1, okay, let's do rare plus 1. Rare is at 4, 4 plus 1 modulo max, what is it? It is 0. Is 0 equal to front? 0 is not equal to front. So you are allowed to move rare here. That is, this Enqueue operation can therefore Enqueue 27 here. A rare moves to this particular location. Right? So you have rare now here. Now do you think you can do any further Enqueues? There are no spaces. That means the queue is full. How do you detect it? Same funda here. Rare is 0 plus 1. Okay. Modulo 5 gives me 1. And 1 exactly is where front is. Right? Front is also at 1. And rare plus 1 modulo 5 is also at 1. So that basically makes me come to a conclusion that yes, this particular formula is correct, through which we can detect a circular queue to be full. That is, if my rare and front are side by side, rare and front are side by side, right? Rare and front are side by side. How do we detect side by side? We can't. So we will say, we will add 1 to rare, and then rear and front will become same because they are side by side. But then we have to be careful. Rear adding 1, anything that you add, right, can take 4 to 0, right? So 4 to 0 has to be done through a modulus. Therefore, we will use modulus everywhere so that this wrap around actually happens, and that's what your useful algorithm will be. So with that, we come to the end of this particular lecture. We will do the solution here for most of the common problems that come in your university questions. Most of them we have already discussed in the lecture. Should not take long, but let's see each and every question. Which of the following data structure can be used to implement queues? And we know that we can use an array, we can use a linked list, both B and C. When we are doing linked list, we will be explaining how an array and linked list are mostly the same in terms of being linear data structures, and therefore they can be used to create a stack, they can be used to create a queue, etc., etc. So both B and C will be the answer to this problem. Write algorithms for push and pop operations of a linear queue. We have already done that, right? So we have completed that here. These are the push operation and this is the delete operation, right? Actually, this is not called push and pop. Yeah, this question is wrong. This is not called push and pop. This is called as either insert, delete, or we can say Enqueue, Dequeue, right? But nevertheless, since they have said linear queue, we should be able to imagine that this is a typo in the question, right? But then that's the answer to that. If we go to this particular problem, it says define queue and its applications. We have defined queue at length in the first portion of this. We have said it is a FIFO, and we have said that there are two areas, one at the rear, one at the front, from where the insertion and deletion takes place. This is something we have discussed also. And if you think about the applications of queues, right, because that's also something that they have talked about. Again, they have asked the same thing, insertion and deletion from the queue. So we have covered that. We'll not touch that. But let's talk about the application for some time, right? Let us say that you have a queue like this, right? You have a queue like this. And let us say this is a CPU. Yeah. So let us say you have this as a CPU scheduling queue, which means that whenever you open an application like Notepad, right, whether it can be opened immediately or whether it needs to wait for others in the queue to be opened first is what this queue handles. So let us say your CPU is at 100%. So it cannot open any further processes till some process gets killed, right, or exited. And you have opened Notepad. So Notepad finds its place in the scheduler queue, right, of the CPU. Because CPU is at 100%, it cannot open Notepad, but there was a request, so it has to be kept in the queue, so that as soon as CPU becomes slightly lower, Notepad will open up, right? So that's why Notepad is enqueued into the queue. Now, after opening Notepad, you think that you should be opening calculator to do some calculations. Again, you do a calculator open, and as soon as you do that, CPU is still at 100%, so it cannot do anything. So the calculator is also queued into the CPU scheduler, right? And because let's say a couple of minutes have passed, you are neither seeing Notepad opening or calculator opening. You press Notepad one more time, right? So you want to actually open Notepad one more time because nothing is happening. So Notepad will come into the queue again. Now at this stage, your CPU has come to, let's say, 70%. Then this notepad will be dequeued, right? This notepad will be dequeued and it will open up for you, right? The CPU is right now at 80%, right? So let's say the CPU has become 80%. When that happens, then this calculator will be dequeued and calculator will open up for you. Let's say the CPU has now become 90%. Still there is some scope, and we will utilize that scope to actually dequeue Notepad, and another instance of Notepad will open and dequeue will happen. The queue will now become empty. So this is dequeued, this is dequeued, this is dequeued. And that's how a queue is used for a CPU scheduler. In fact, for any kind of queue like a printer queue, keyboard buffer queue, network queues, these are the applications. So this, let's try to solve this problem, what it's trying to convey. Circular queue is implemented using an array of size 10. Let us draw that. Let us draw this circular queue, an array of size 10. Okay. Let me see if I can draw 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. Array index starts with 0. Front is at 6. Front is at 6. Front is here. Our front is here. And our rear is here. Rear is at 9. When do you think the next insertion will happen? Front is at 6, rear is 9, means queue is going in this direction, anti-clockwise. So there is 1 person in the queue, 2 person in the queue, 3 person in the queue, 4 person in the queue. There are 4 persons in the queue, 6, 7, 8 and 9. One more insertion means that rear will have to move forward. And rear will have to move forward means rear will have to follow this formula, if you remember, right? That's what we have done in a circular queue. We have to reset rear to 0 because it is crossing the index of the array. And that's what we do with modulo. So rear will move forward to 0. The insertion of the next element will take place at the 0th index is the answer. Next, state the difference between stack and queue. Very simple. I'm sure you know by now that last in, first out, or first in, first out can be a difference. Insertion is performed at the top, it is performed at the rear, deletion is performed at the top, performed at the front. Right? Of course, these are the two definitions or two distinguishing features that without even understanding or rather without even remembering anything, it will resonate because you know now that queue has two ends, a stack has only one end. So I'm sure you can give these three differences, right? And we have discussed the applications, you can give this difference also. The rest, you can always read it out and produce it at the time of the examination. But I don't think without reading also you can probably answer this question very easily because you know the properties of a queue, you know the properties of the stack. Just write it down in the point, in terms of points, you should be good enough. Why circular queue is better than a simple queue? Of course, we know the answers. Let's see. It reuses free space. We have seen that. There is a pocket created due to the dequeue operations. Front is moving front. It is leaving behind some space. And rear is coming back and filling that space. So it reuses the space. Continuous Enqueue Dequeue possible, right? We can keep on doing Enqueue Dequeues. Remember in linear queue, we said that once we have Enqueue till the last, once we have reached rear, right, we will not be able to insert any elements even though we do dequeues because rear is pointing to max minus 1. But here we can, right? If we have reached rear also, if we do a dequeue, we can do another insertion. If we do one more dequeue, we can do another insertion. Every dequeue, we can do an insertion. So we can do a continuous Enqueue Dequeue. And we don't need to shift after deletion, right? Sometimes some queues, if you see, does this. That's another algorithm of queues. So some queues, if you see, what it does is that suppose you have these elements here, right, in a queue. So this is your front and this is your rear, right? So now if I say that I will dequeue this element, then what do some algorithms do? They push this element here. They push this element here, push this element here, here, and here. So your new queue, therefore, looks like this. 9, 11, 29, 5, 6, and a blank element. So what are you doing? You are actually pushing all elements and your front does not move forward. Your front was here, front stays here. Only your rear was here, rear moves forward, right? Or rather, rear moves backward. So what are we doing here? This is actually a physical reality queue where the front remains at the front, right? The front person moves out and the entire queue moves forward. That is what is happening here. But to move the entire queue forward, you will have to do n iterations. So the time complexity that you were actually doing it under order of 1 now becomes order of n. And that's the disadvantage of doing this model. So it says that no shifting needed after deletion is one of the important aspects of a circular queue, right? So we can now understand what this statement means. Ideal for scheduling buffers, yes, we know that. Write an algorithm to delete an item from a circular queue, so you have to do a dequeue. Also find the complexity, we have done that. I think this is the last question that we have to cover. And suppose a queue is implemented by an array. Write an algorithm to insert a new element on the kth position of an array. So let's say a queue is implemented through an array. So let's say this is that array, right? Let's say this is 79, 69, 5, 4, 29, 7. So what are we seeing here? We are seeing that kth position of an array. First of all, a queue always has the exit from the front and always has an entry from the rear. And we are saying entry, insert a new element at the kth position. That means somewhere in between. That is not possible. So we are defeating the basic nature of a queue through this problem statement. Therefore, we are not going to consider this as a queue. We are going to consider this as an array, a simple array. In a queue, you cannot insert an element at the kth position. Hence, we are not considering it as a queue. We are considering it as an array. I hope that makes sense. And if I therefore take the kth position as, let's say, the 4th position, then I'm trying to insert it here. This is my 4th position or the 3rd index. Right? So I'm trying to insert an array into my 4th position or the 3rd index, and let me just increase this size of the array so that we have a sizable array to work with. Right? So let's say this is 6, 7, 8, 9, and all of these are blank pockets. So what we have to do is that we have to make this element free. Right? If we have to insert at this position, we have to make this element free. Means that we have to move this element to the right. Then we have to move this element to the right. And then we have to move this element to the right. Now this element will become free. Therefore, we should be landing up in this particular situation. Right? So we should be landing up in this particular situation where zero, 1, 2, 3, 4, 5. Not sure where we went wrong, but we can renumber it again. Right? So what we are doing is we have freed this, and whatever those elements were, I don't remember them, but I'm sure you can understand it doesn't really matter. So we are actually moving these elements to the right of that array. So let's say these were the elements, and 29 was originally here, 7 was originally here, 30 was originally here, 9 was originally here. We have moved those elements to the right. This is what we need to achieve. And when we achieved it, then we can insert our target element. Our target element, let's say, will be 99. We can insert that 99 here if we achieve that. That is what we have to do. So what we will do is from a drawing perspective, we will draw the original array so that now we can trace that array as we write the code, right? So we will draw the original array. Again, I don't remember the elements, but we will put arbitrary elements so that we can track it now. 7, 6, 79. Let us say these are the elements. Let's make this 89 because I already have 79. Now I was saying that we will insert here. So if we want to insert here, then our job is to track the, so our job, step 1, we are supposed to write an algorithm. So we will take let's take n as equal to the size of the array, or I would say not the size of the array, the max element index of the array, right? So if n is the max element index, then my n is actually equal to 6 right now. So what we will do is, we will say that n will go from 6 to k minus 1, because k is 4, which is the position we are interested in the index, so it will go to k minus 1, right? So from 6 it will go here, 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 in terms of decrementing the index positions, right? So from 6 it will go to k minus 1, which is basically our 3. This is going to be 3, right? With a step of minus 1. And in this stage, in this loop, what it will do is that if we call this as ARR, then it will say that ARR of n plus 1, right? Max element index is at 6, right? Max element index is at 6, n is here, n plus 1 will be here. So at this position, we will have to move the nth value. So we will have to move at n plus 1 the nth value. So 89 will therefore move here. Right? Next, the loop will go to step minus 1. Max index has moved to 5. Right? It started with 6, step minus 1 means it will move to 5. And at the fifth position, so 6th position will be equal to the 5th position. So we will be having 6 here, and this will become empty. Now it will become 4, and that 4 plus 1 is 5. 5th position will become the 7th position. 4th position rather, 7 will move forward, and this will become empty. And then n will become 3. N will become 3. N plus 1 will become 4. So ARR 4 will have 29 now, and 29th position will become free. And at that free position, our step 2 will fire, and step 2 will say that ARR of n, because n has decremented and reached till k minus 1, right? So L has decremented and reached till k minus 1. We will assume that we are writing that after a proper check that n has not incremented further or decremented further down to come out of the loop. Even if it has come out of the loop, we can make an adjustment that n becomes equal to k becomes equal to k plus 1. Ultimately, we are having k at the right position is what the assumption is. So ARR of k is therefore equal to rather not ARR of k. Yeah, we can write k if we write it as k minus 1. I think that would be better. We can say ARR of k minus 1, which is the 3rd index here, will be equal to my target, which is 99. And therefore 99 will come here. So this is how you are actually creating a space for that particular insertable element, and therefore moving it forward one step at a time till the space is created at the position of insertion, and then you insert that element. The order of complexity of this is going to be order of n, because depending on the size of the right hand side, which can be n, you will have to spend that amount of cost in terms of time. So with that, we come to the end of the basics of queue, which is basically we touched upon linear queue and circular queue, and we will be further touching upon the priority queues and the DQ part of it, which would complete all the 4 different types of queues, and then we will complete the common questionnaires, and that would actually mean that we will complete unit 2 that we had planned to complete. Till the time we meet next, I'm sure you would have ample to read now in terms of things that you can probably go through. My honest request is go through them, keep practicing. Programming is like mathematics. As and when you practice, more you practice, you get expertise on it. So keep practicing, and till the time we meet next, happy days, happy holidays. Thank you.